All right, so let's talk about the Winnow algorithm. The Winnow algorithm is an online learning algorithm similar to the perceptron. This one was designed by Littlestone, and again in sort of prehistoric times for machine learning. But the idea with algorithms like Winnow, so Winnow is part of a family of algorithms, and AdaBoost belongs to that same family. With these algorithms, the idea is that you should interpret the coefficients as sort of weights on the features. Okay, so let me just show you an example. So W1, let's say xi1 plus W2 xi2, and so on and so forth. Right, this is the function f of x. And the idea with these algorithms is that you want to find the coefficients that are the best at predicting the label, and those guys should get high weights. And the coefficients that are not very good at predicting the label, you essentially get to wipe them out by setting their weights to 0, so it wipes out the whole term. Okay, so let me show you how that works here. All right, so the input to Winnow is data, but also a parameter, and it's called Ada. Okay, and I'll tell you how to choose Ada later, but we're going to leave it flexible for now. Okay, so we start by setting the weight vector at time 0 to have all of its elements be just 1 over p, where p is the number of features. Okay, so all of the features get equal weights, but you're probably wondering why I didn't just set them all to 1, and it's because the weight vector actually is going to be kind of like a discrete probability distribution. It's going to be exactly a discrete probability distribution. And so they all need to add up to 1. Okay, so since we don't know which features are better than other features at the beginning, we give them all equal weights. Okay, so now at each iteration of Winnow, so again, it's an online learning algorithm, so you get one observation at a time. You deal with one observation at a time. Okay, so what we'll do is, again, now let's locate a point that's misclassified. So locate an observation such that it's misclassified, y times w at that time. Dot x is less than or equal to 0. Okay, and if there are no points like that, of course you're done, because it means you have no misclassified points. And in that case, you would stop, and you would output the weight vector at that time, because you were done. And if you did manage to find a misclassified point, you would update the weight vector in this very interesting way. And I'll explain this update in a minute. Okay, so you take the weight vector, and you multiply each element of the weight vector by something that looks kind of like this: e to the Ada yi xij. Okay, so I'll explain that in a minute. And then the denominator, there's a denominator called zt. Zt is a normalization factor, because remember, I told you that the weight vector at each time should be a discrete probability distribution. So, so zt actually is just making sure that that happens. So it's just the sum over all of the elements in that vector, so that it all adds up to 1. All right, so let me oh, and then the end goes here at the end. Took up a little more space than I planned. Great. Okay, so the idea then is if you find a misclassified point, okay, and then you reward the features that agree with the label. Okay, so if the sign of that feature for observation I equals the true label, then that means that feature is good at predicting the label. Okay, so then what you do is you reward that feature by increasing its weight. Okay, and so to do that, you would say actually I'm going to write proportional too, because I'm not going to include the normalization constant. So then Okay, wjt plus 1 is proportional to wjt times this weird factor. Okay, but what's the weird factor? Well, it's e to the eta times, and then yi times xij, right? Yi times xij. And then we've decided over here that that is positive. So this is actually something positive. Okay, so what happened? Well, you've multiplied wjt by e to the, but you multiplied wjt by something that's bigger than 1, right? So that means you've increased the weight vector for the next time, okay? So because the sign of xi agreed with y, you've increased its weight. Okay, now, and the other is true too. So if the sign of xij does not equal y, you would punish it. Okay, so you'd punish it. So wj t plus 1 then is proportional to wj t times e to the negative, and then this thing then is going to be negative. Okay, so you punish features that disagree with the label. Okay, cool. And that's how it works. It just repeats itself over and over again. And the features that are really good get rewarded a whole lot of times, and the features that are not really good and don't agree with the label, they get punished a whole lot of times. And after a while, the features get punished so many times, the bad features get punished so many times that the weight vectors eventually become 0. And so they get totally wiped out. And the only features that remain in play are the ones that actually agree with the label. And so that's how the algorithm proceeds.